Guten Tag, wie geht es Ihnen? Hola, ¿cómo estás? What's going on, Super World? Okay, we are back better than ever. Right, so today we are going to finish up gas laws in chapter 10. We have to deal with velocity of particles. We have to talk a little bit about Graham's law of effusion, differentiate between effusion and diffusion, and then we have to talk a little bit about the van der Waals equation. So let's go ahead and get started. Let's deal with velocity of gas particles first. So the average translational kinetic energy is directly proportional to the absolute temperature. Okay, so we know this already. So we know that as the temperature increases, the translational kinetic energy of the gas particles is also going to increase. All right, so now let's just look at a couple graphs here. All right, and let's label this kinetic energy, and let's look at proportion of molecules with specific kinetic energy. All right, so this is a sample of gas. So if we were to measure the kinetic energy of all the gas particles in a sample, we would get this type of curve. All right, so we'd have a nice steep, and then it kind of comes off down here at a slow angle, something like this. All right. So if we were to look at this curve, the most probable kinetic energy is right up here at the top. Okay, so this would be the most probable kinetic energy. But it's not the average kinetic energy because this is skewed to the right. Right? So when we look at the graph, the most probable kinetic energy is not necessarily the average kinetic energy. Okay, so the average would be somewhere over here. It's okay because this big tail over here and this steep slope on this, it pulls the average this way. So somewhere in here would be our average kinetic energy. They're not necessarily the same. So let's write that. The most probable kinetic energy and the average kinetic energy are generally not the same because of the asymmetric distribution of kinetic energies. Now, we often use something called the root mean square speed when we're talking about gases. So when we talk about the root mean square speed, what that means is the speed of a gas molecule having the kinetic energy equal to the average kinetic energy of the sample. Okay. So the root mean square is dealing with the kinetic energy of the particles right here at the average kinetic energy. But it's really just giving us the speed of the gas particles. All right. So we know we have a formula for kinetic energy. We know that Ke is equal to 1/2 the mass times the velocity squared. Well, we're dealing with gas particles, and for the velocity, we're going to use that root mean square. So kinetic energy is equal to m root mean square squared. Well, how do we calculate this root mean square? Well, we can really rearrange this. Okay, so we can rearrange this equation. Okay, because this is what this speed or this root mean square is really what we're trying to look for when we're talking about gas particles. Right, so we can take this equation and manipulate it. And we can end up with our root mean square equal to the square root of 3RT over mass. Now, the R that we need to use is 8.31 kilogram dot meter squared. Seconds to the -2, moles to the -1, Kelvin to the -1. T stands for temp, and it's got to be in Kelvin. M is molar mass. And our root mean square is really our velocity in meters per second. Well, what is this really telling me? Okay, so what this is doing is it's letting us compare gases with different molar masses. And if we were to look at this equation, the average speed of the gas particles is inversely proportional to the square root of the molar mass at constant temperature. Okay, so if we're really what we're saying is if we're comparing two gases' particle speed, okay, at the same temperature, all right, well, this really stays the same because the temperature is going to be constant, the R is constant, the 3 is constant. So when we're comparing the two gases, this is all going to be the same. What's really changing is my molar mass, and it's a square root. So what is that, again, what is that saying? So the higher the molar mass of the gas, the lower the average speed of the particles at constant temperature. So the bigger the molar mass, the slower the particles are going to move. Go ahead and try one. Try a couple of these. Let's calculate the average speed of O2 molecules at 25.00 degrees C. Okay, so our average speed is equal to the square root of 3RT over M. So we have 3 times 8.31 kilogram meter squared dot second to the minus 2 dot mole to the minus 1 dot K to the minus 1. Right, that's got to be in Kelvin, so it's 298.00 K, all over our molar mass, okay, which is, needs to be in kilograms per mole. Why does it need to be in kilograms per mole? Because our constant's in kilograms. So this, instead of grams per mole, this has to be in kilograms per mole, right, which isn't a big deal. It's still just 32.0 times 10 to the minus third kilograms per mole. So you just find the grams per mole and convert it to kilograms per mole. So when we do this math, the average speed of the O2 molecules at 25 degrees Celsius is 482 meters per second. So let's just go back a page, all right, and let's write it in here that this has to be in kilograms per mole. Your molar mass has to be in kilograms per mole. But it's a simple calculation. Now, what's nice is we can use this to actually compare speeds of gases. So let's do that. Consider the following gases. We got helium and chlorine and methane and ammonia. Rank the average speeds of these gases if they have the same temperature. Okay. Well, if we look at the equation, when we're using this equation here, this is going to always be the same for all of them. So we can really simplify this down. Okay, since this is all the same, we really could just do this. Now, what is that telling me? Okay, this is just telling me, okay, that the larger the molar mass, the slower the gas particle will move. So I need the molar masses of these guys. That's all I need to do. So if I figure out the molar masses, okay, helium is 4.0 grams per mole. Chlorine is 16. Whoops, no, it's not. Chlorine is 71 grams per mole. This is 16.0 grams per mole, and then ammonia is 17.0 grams per mole. Okay, so now that I have this, okay, helium would be moving the fastest. And then our next one would be CH4. And then NH3. And then finally our chlorine. So we can rank them, okay, by using this quick little formula, but in reality, you don't even have to do that. All right, if we're at the same temperature, we're just comparing their molar masses. Pretty easy. Okay. Let's get Graham's law of effusion. Now, effusion and diffusion are not the same things. Effusion and diffusion are not the same things. Excuse me. Effusion is the flow of a gas through tiny pores or pinholes. In general, the larger the mass or molar mass of the gas particle, the longer it takes to effuse. Now, why is that? Okay, so let's say that we have a hole. Okay, and we have gas particles on this side. All right, effusion is the rate at which it'll go through this tiny hole. Now, if I have a very small gas particle, okay, to go through there, it's got all this space. It's got all this space. There's a lot of space for it to go through. But if I compare that to this guy, all right, it's going to be a lot harder for him to get through just because he's so much bigger. All right, which means it's going to slow down the rate at which it goes through those holes. Now, there's an equation. And it lets us compare this rate of effusion with two gases. So we got our molar mass 1 over molar mass 2 square root equals the rate of effusion 2 over rate of effusion 1. Let's go ahead and try it. Helium leaks through a small hole at a rate of 3.22 times 10 to the minus fifth moles per second. How fast will oxygen effuse through the same hole? Well, this becomes a pretty easy problem. Take the square root of the molar mass of helium, the molar mass of O2 equals the rate of O2 over the rate of helium. Well, the molar mass of helium is 4. 32 equals the rate of O2 over 3.22 times 10 to the minus fifth moles per second. When we do this math, our rate of oxygen is equal to 1.14 times 10 to the minus fifth moles per second. Now, oxygen is much heavier than helium, so this rate better be slower than this one. And it is by quite a bit. But it's just a simple way to compare those, that effusion rate. Well, why do we care about effusion? Well, there's a direct correlation with diffusion. So what's diffusion? So diffusion is the movement of one gas into a container already filled with gas. So we know that all gases will expand to fill their container but depending on conditions, they will do so at different speeds. Now, in reality, we can use the effusion equation for diffusion. It's not exactly right, but it's close enough. All right, so the effusion equation will also work for diffusion. So now what does that tell us about diffusion of gases? Well, the larger the mass of the gas particle, the slower it will diffuse. Now remember, okay, what happens to the velocity of our gas particles as it gets bigger, right? So as our gas particle gets bigger, the speeds slow down. So it really does make sense that it's going to diffuse slower through that gas. Right? Good. So that's diffusion. And I'm not going to do an equation. I'm not going to do a formula because you could use the formula. It's the same thing. And the last thing I want to talk about is what van der Waals did to the ideal gas law. Okay, so van der Waals modified the ideal gas law to make it more reliable using real gases. So we've already talked about this, but remember there are issues with the KMT and real gases. So just for review real quick, in real gases, okay, they have volume. KMT says they don't have volume, all right, or it's negligible, right? So that's one issue. Another big issue is real gases have attractive forces. KMT says that they don't, all right? So real gases have some issues with the KMT. So what van der Waals did is he looked at some of these issues and he changed, okay, or he modified the ideal gas law. So what he said, look at PV equals nRT, right? There's a problem with the volume here, okay, with the KMT, because we know that those gas particles have that, all right? And when we're talking about pressure, those attractive forces play a role in that pressure, right? So what he did is he took this equation and he changed it to this. Pressure plus n squared over A divided by V squared times V minus Bn equals nRT. Now, what he did is he came up with an equation to help us overcome some of these issues. Now, in reality, you're not going to have to use this equation, right? You are going to have to tell me what it means, though. All right, so this right here, this n squared A divided by V squared, it accounts for the strength of the intermolecular forces. This Bn excludes the molar volume of the gas particle. So this modifies it so we get a little bit better equation. All right, you need to know what these mean. Okay, you need to know what those mean. Okay, you're not really going to have to use it, but you're going to have to know what they mean. Now, I want to show you. Okay, I just want to show you how it would be used. If oxygen was an ideal gas, 1.00 moles at 0 degrees C in 22.4 liters would have an exact pressure of 1.000 atmospheres. We know that if it's a real gas, if we have 1 mole of it at 0 degrees C, right, at standard temperature in 22.4 liters, it should have an exact pressure of 1.00 atmospheres. Right? Well, what does it have? So if we use the van der Waals equation, okay, what is the pressure of oxygen? Because oxygen is not an ideal gas, it's a real gas. So let's use the van der Waals equation to calculate the pressure if A equals 1.382 liter dot atmospheres dot mole minus 2, and B equals 0.03186 liter dot moles minus 1. Right? So they're giving us the A and the B. All right, well, let's see what it does. P plus N squared A over V squared, V minus B N, equals nRT. So we're trying to figure out this pressure. So we have P plus N is number of moles, so we got 1.00, and that's moles, and that gets squared, times 1.382 liter dot atmospheres mole minus 2 all over 22.4 liters, and that's squared, minus times 22.4 liters minus 0.3186 liter moles times number of moles, which was 1.00 moles. That equals N, which is 1.00 moles, times R, or an atmosphere, 0.08 8. So we'll just use 8.2 times 273K. Wow, that's a pain in the butt. When we end up doing all that math, our pressure ends up being 0.999 atmospheres. Does it make a difference? Well, I guess. I mean, okay, just using PV equals nRT, we said it would be 1.000 atmospheres. Doing all this math, yes, it makes a difference, right? But not very much, all right? So in reality, we're not going to use this equation, all right? You just need to know what this guy means and what that guy means. All right, that's where we're going to end for today. Have a good afternoon.